Okay, today what we're going to do is we're going to start putting things together and solving trig equations. So it's taken almost 6 weeks of learning the fundamentals to get to this point. What you've been practicing was verifying identities, and the main emphasis, at least I think the value in that, is to help you see the algebra patterns in there to be able to simplify complex, complicated looking expressions. So now what we're going to do, instead of looking at an expression and simplifying it, we're actually going to make a complete sentence out of it, which we call an equation in mathematics, like usually when there's an equal sign in it. And then we're going to learn how to solve, using our trig skills, solve different kinds of equations. And obviously, just like back in your algebra background, there are simple type of equations, and you know certain techniques for solving certain types of equations, and then you can get more complicated equations. And then, of course, the real reason for all of this study and learning is because you're trying to learn how to solve practical applications, how to be able to use this mathematics in practical ways. Okay? So what I'd like to do is to start out with some relatively simple equations, and then we're going to split this up into segments for the internet access, but I'm probably going to actually be mixing these things together as we go through this stuff today. All right. Why don't we let's just make up an equation, something relatively simple. What trig function do you want to use? We've got 6 of them available. Tangent, okay? So let's say we say the tangent of, how about 2 theta minus, how about, let's make it real easy, equals 0. Okay? Nice complete sentence, a simple thing. Now, when you see a simple equation like this, I'd like you always to try to have a graphical sense of it if it's relatively simple. Okay? And what I want you to do is to go back to previous stuff that we studied where we studied the graphics. Think of that as a function. Think of that as a function. Now, if you've got your fundamentals down, you can quickly realize that you're dealing with a tangent graph that has a period normally of what? What's a tangent normally have a period of? Pi, right? So the normal period on a tangent graph is going to be pi, but this factor of 2 right here, that's kind of like your omega that we've seen earlier in the course. And so the period then is going to be adjusted by dividing the fundamental period of tangent, which is normally pi, by that number. Okay? So that's usually the first thing you do, is to figure out what the period is of your function you're trying to graph. And then next, you're going to see that, okay, we're going to lay this out, and remember what a tangent graph looks like. Looks like this, right? And the period is the distance, one cycle of it could be thought of as between those symmetric asymptotes, right? Normally they would be at pi over 2, negative and positive, right? But what are we going to do to them? We're going to make that distance, instead of it being pi between the asymptotes for a period, we're going to make it pi over 2. If you split that in half, then that means this asymptote on the left is at minus pi over 4. And the other one over here is at pi over 4. Right? You've all done this earlier. And then we're going to do what with the graph of the normal graph of tangent then that would fit in here? Take it. What's that subtracting 1 do? It lowers it down 1. Okay? So that's a transformation down 1. And what this 2 does is it actually did a compression, didn't it? A compression on the graph made it half as wide as the original. So what you're going to do is you're going to take a tangent graph and you're going to lower it down 1, and you've also squeezed it in between these closer asymptotes now. So you're going to have a tangent graph that's going to be doing this kind of a thing. And this y-intercept is going to be at what? 0, negative 1. Right? Okay. When you build a graph mentally like this, what I want you to always do is to come back and check, find a point that you're comfortable with, like this 0, -1, and check it in your function. So if I go up here and look at f of theta, and let theta be 0, let theta be 0, and try it in here, we're going to be getting the tangent of 2 times 0 minus 1, and the tangent of 0 is what? What's the tangent of 0 radians? 0, isn't it? And so you get an output value of -1. That fits. You also know characteristics of a tangents graph. If you're on the what was normally your 0 here, right here, you know that if you go halfway over to that asymptote, you would be normally up at 1, wouldn't you? Like at 45 degrees on the original. But then, since this thing got squeezed in, it should make sense to you that if you come over halfway to this asymptote at pi over 8, that should be giving you a value of 0 right there, right? For the y value. Let's try that. F of pi over 8 in your function up here. Put pi over 8 in here, times 2 is, 2 times pi over 8 is pi over 4. So you're going to have the tangent of pi over 4 minus 1. But the tangent of pi over 4, you know, is tangent of 45 degrees? 1, isn't it? 1. So you get 1 minus 1 is indeed 0. See that? That's the kind of graphing skills that I hope you have. Now, back to the problem. Here's the equation. We just built it graphically, didn't we? And what's the answer to the question? Where is this equation? What value of theta, that's your unknown, what value of theta makes this whole thing equal 0? Pi over 8. Pi over 8 from the graph. Okay, so that's a graphical perspective that you can quickly kind of have a sense of, on a simple equation like this, of what the graphical solution would be. Okay? Now, how many answers would there be? Only one?
Negative.
No, there's a family, aren't there? There's a family of these things, right? They keep on going. And how often do they occur?
Negative multiples or odd multiples.
How often are these points where this value here, see, think of that as your y value, where it's equal to 0. Well, it occurs right here, and every period to either side, multiples of that period to either side of this, right? So from the graph, we're able to see that the solution set is the set of all theta such that theta equals pi over 8 plus
A constant times pi over.
a constant, an integer multiple of the period, right? Adding the period or subtracting the period, and it could be twice the period or 5 times the period to the right or to the left, right? So how do you write that? K times pi over 2. Good, Tom. Yep. So here's a solution set for that equation right here. Graphically. Let's do it analytically. Do it analytically. So the way we do it analytically, and that means by pencil, paper, or marker, okay, on the board, is we solve this equation. Now, just like you've seen back in beginning algebra, typically most problems, most equations, you isolate the expression involving your unknown, and then you're trying to release the unknown from inside this function, right? So what you'd normally do is you'd say, okay, 2 theta is equal to the inverse tangent of what? Right? The angle here is equal to the inverse tangent of this ratio value. Back when we were studying the inverse characteristics earlier. Right?
Right.
Okay, now let's answer this. You have to have knowledge of an inverse tangent function separately, don't you? Inverse tangent function. And the inverse tangent, you know, I hope. Let's go back and do a quick microscopic review, a real fast review. Here's a normal tangent, right? And you know the ratio value is 1 when the angle is normally, what? Pi over 4. Or 45 degrees, right? Right? 45 degrees. Or multiples of their period, right? So what you're going to get, because this inverse tangent function here is actually this function. Here's a graph of the function, of the inverse function. Inverse tangent of x versus x. And when the ratio in here is 1, the output value here is pi over 4, or 45 degrees. So what you're going to say is you're going to answer this thing right here with a function value, which you know is pi over 4. So you get 2 theta equals pi over 4 from your inverse trig function, right? And then you know, in the real world, though, there's multiple cycles of tangent that occur. And how often will another correct value show up? You can even think back to unit circle. Right there, right? At 45 degrees or pi over 4 radians, the tangent value there is 1, isn't it? And it also occurs here, doesn't it? And every multiple of pi, right? Every multiple of pi. So since we know this value right here is pi over 4, then if we add to that k pi, where k is an integer, 0, 1, 2, 3, 4, 5, minus 1, 2, 3, 4, 5, etc. That would give you an answer for this 2 theta thing. Now, if you divide both sides of this, look at this. Actually, an easier thing to do is multiply both sides of this equation now by 1/2 to figure out what theta is. Multiply both sides of this by 1/2, and this turns into theta. This becomes half of this is pi over 8, plus multiply this by 1/2, k pi over 2. An infinite family of answers, which agrees with the graphical approach that we saw earlier. Any questions? This is the analytical approach, and over there we did the graphical approach. I saw a little bit of confusion back there. Elizabeth?
No, I got it.
Oh, good. Okay. All right. Anybody else bothered by this? Brooke?
Yeah. It just seems like the only.
Is this thing bothering
It's
you?
all pretty much. No. The only thing that would be different, well, not the only thing, but the pi over 4. I guess I just need to see another problem. Just
Okay.
to put it all together.
What if this was just given to you and said, hey, what's the inverse tangent of 1? As a separate problem. Forget about all the rest of this stuff. You know that's an angle.
Yeah.
You know that's an angle. And if you're confused by this, then another way to write it to help you understand it is to think of another expression that gives you, says the same thing, that the tangent of the angle is 1. And you know that that angle is pi over 4, or 45 degrees, right? Okay. So that's what's going on right here. So you figure out what this piece is, which is pi over 4, or 45 degrees is fine. And then you know you could add to it multiples of the period. Okay, multiples of the period. Integer multiples of the period. So you get an infinite family of answers out of these things. Okay, let's do another one. Let's grab one out of the book. And before I do that, one thing I think I should do is, remember I've joked with you earlier in the course that you don't need the answers in the back of the book to check yourself. You can solve a problem graphically like we just did on the board to sort of check yourself, or you can grab your calculator almost all the time and check yourself after you've done the work. So what I could do with my calculator is, let me go ahead and put the calculator in degree mode, which it happens to be in right now. Okay, we're in degree mode, looking good. And if I quit, what I could do, a couple ways of doing this, is one way is I could put the function in here, which says that the tangent of 2x minus 1 is the equation, and we're looking for the x-intercepts of this, are we not? The x-intercepts. So why don't I set a window based in degree measure now? X is our degree measures. And so why don't we go from, say, minus 100, let's say minus 90 degrees to, let's say we go as far as 180 degrees, and let's put tick marks every, think about the problem we did. Pi over 2 is what you probably normally do for just a plain tangent, but remember we're doing tangent of twice theta. So probably every 45 degrees maybe, okay? So every pi over 4. So let's use pi over 4 there. And then vertically, I know the graph is shifted down 1, so let me make sure I go low enough to sort of see that stuff, and then above the x-axis. So let's go down to, say, minus 3, and let's go as high as, say, 2, and put tick marks every 1 there, and see what the graph looks like. Don't be bothered by the fact the calculator is really not drawing an asymptote. It's trying to connect a pixel value up here, a positive pixel value, and then as it moves 1 pixel to the right, it's trying to then draw another pixel value that gives you a point which now happens to be negative. And so it fools you. It actually, you think that's a vertical asymptote there, but you can't actually get that drawn here in function mode. But the key is looking at this 0 right here and how often these zeros occur. So what we could do is we can test this by using the work that we did earlier. Actually, let me go back to the graph and let's turn trace on. And at 45 degrees, I'm actually going to be right here. And something's wrong here on my x-axis. Oh, I know what happened. See that wide bar right there? What mode am I in my calculator? Degree measure. And what did I do on my window settings? I use radian measure. Look at that. It's going from minus 90 clear out to 180, and it's putting that little X tick mark every 3/4 or so, right? That's why it looks like a double or an extra bar there. So what I'll do is I'll change that setting to be, what did we say? 45 degrees, I believe, right? Okay, now it should look much nicer. Here's 45 degrees. There's negative 45, etc. And so look, there's your value right there. And if you turn trace on now, if you turn trace on and we punch in pi or half of 45, right? Right. 45 divided by 2, we all know that's 22.5. Bingo, hits a 0 for us. And then there should be another one over here, shouldn't there? If I did what to this 22.5 degrees? If I added, I'm still in trace mode, 22.5, and if I add to it the period, which is pi over 2, but in degrees it's 90, isn't it? If I add 90, I should hit another 0, shouldn't I? Oh, look at that. You got that. Did you see that? They got a little picture of me up there. So check this out. The 22.5 plus 90 degrees is 112.5. And then, again, another 0. Okay? So you see how you use your calculator to graphically solve that? Check this out. I don't know if I've done much of this with you. We can solve an equation, can't we? There's an equation solver built into the calculator. And where is our equation stored? I had graphically put it in Y1, hadn't I? Okay, so watch this. You go to math on your calculator, and these are a bunch of different things that we can do in math. And then if I go up arrow instead of down arrow, it takes me to the bottom of the stack and it sets me up with a solver. If I hit enter right there, it then, if I up arrow, it takes me off of this X reading and it takes me up onto the equation. Let me clear that because you may have something looking like this on your calculator. So what I did is I got to the equation solver under the math window or screen, and then I got the solver active, and then I up arrowed to get up to the equation. And then what I want to put in here is I could punch in tangent to x, subtracting 1, and I want that equation to equal 0. When you hit enter, then, the other thing I could have done is done what right here? What could I have put here instead? Y1 from the variables list if I chose to, because I had the equation stored in Y1. So then I hit enter, and now it's sitting here. Here's my equation on top, and right here it's sitting and asking me to make a guess. So based on our pencil and paper work, I'm going to guess, why don't I guess, say 20 degrees? Let's say I did just my hand sketch, and I'm not sure. But based on the trig that we did earlier, I'm going to guess 20 degrees. And then I now have to find the solve key, which is down on the enter key on the bottom right of your calculator, if you use the alpha key to get to it, where it says solve. So alpha, enter, and it's now working, and here's our answer, 22.5 degrees. Round that off. There's some numerical round off in there. Okay, so we did a graphical solution with the calculator and confirmed our work on the board, and then we also just ran an equation solver on it. Let's do one more simple equation, and let's do one like similar to what you might see in your homework. What if we have one like number 47 on page 493, it says secant theta is equal to -4, and we are looking for answers on theta in the domain from 0 to 2 pi, the half open interval, 0 to 2 pi. Okay. Graphically, quick review. Remember what a secant looks like? Rides on what? Rides on cosine, doesn't it? Rides on cosine. So if I draw myself a cosine wave from 0 out to 2 pi, it's that quick. The secant rides on that wave, does it not? So its graph is going to look like a 0 on the cosine. You're going to be dividing by 0 on the secant then, and that means that's a vertical asymptote. We've talked about this before. Similarly over here at 3 pi over 2, and the graph takes a ride on there, and we're including 0 in our domain, and we're going as far out as 2 pi, are we not? Open interval on the right end at 2 pi. And don't forget the bottom part of this right here. I'm always take you back to fundamentals because I don't want you to forget what we did a couple weeks ago. Everybody okay? So, where is the graphical solution to this sit, this equation, on this picture? Where's this output value, this y value here? Where's this y value equal to -4? Come over and look at the picture. Help me. I see some puzzled looks. Huh? What's this value, what's this y value right there?
1.
And right here? Those are 1, aren't they? And -1 right there? So where's -4?
It's in between that somewhere.
It's down here, isn't it? Okay, it's down here. 1, let's see, 2, 3, 4, -5, right? -4 is down there. So that keeps going, doesn't it? So here's your answer. Just a touch past 90 degrees, isn't it? A touch past 90 degrees or a touch past pi over 2. Oh, and look at this. There's another one over here just before 270 degrees. Right? Similarly to that thinking, so there's your answers, right? Similarly to that thinking is instead of thinking of the equation as secant, what might be more comfortable for you? Think of it as cosine, right? Think of it as cosine. What's the cosine of theta equal to? Help me. Quick. -1/4, isn't it? Reciprocal, right? Reciprocals. Reciprocal of -4 is -1/4. But we're now talking about a graph of cosine. Where is -1/4 on this picture? Steve?
On negative, like,
This way or this way? No. This is an output value, isn't it? It's the value of the cosine. It's the y value. -1/4 is right there, isn't it? 0 on that domain. -1/4 is right there, and come over here to where you find your cosine reading. It's right there, just a little bit past 90 degrees or pi over 2, and similarly over here just before you get to 270 degrees or 3 pi over 2 radians. See how those tie together? Okay. So then, let's analytically see if we get answers that fit with that graph analytically. So what do we do here? We think of solving this problem for the theta, and what do you have to do to both sides of this to get theta equals?
multiply both sides of it.
What you're really doing is you're applying the inverse function to both sides of the equation as a process. And what happens here is these essentially undo each other, don't they? And they release the unknown that's tied up inside that function. So theta is equal to the inverse cosine of -1/4. The inverse cosine function, keep going back to fundamentals. This goes as high as pi, starts down here at 0, domain of 1 to -1. And what we're doing here is we're coming in with a cosine reading of -1/4 right there, which is sitting right over here, right there at -1/4. And you come up here and just past pi over 2 is where this answer is going to sit. And be aware that there's other answers that are going to show up here, just before you get to 3 pi over 2. So it gets a little tricky here to be able to get there's a pair of answers, aren't there? come back to the graph, there's a pair of answers we're seeing that occur between 0 and 2 pi. There's a pair of answers, and you got to be careful to be able to capture both of those answers. So to make a long story short, we're going to need our calculator on this, but here is the analytical solution, because we're going to need our calculator to do this. Here's the correct analytical solution. This is going to be one answer, and this answer is going to be which one of these on this picture here? It's going to be this guy right here, isn't it? It's going to be that answer. And then there's another answer, though, that is at, how are we going to get that other answer? We got to do a little arithmetic, don't we? Don't we have to take this reading right here, which is a little bigger than pi over 2, and we have to do something to get ourselves to that spot. Oh, look at this. Couldn't we come over to 2 pi and subtract off that value? Wouldn't that be the same physical distance as this? Yeah. By having the graph, you can see where these other answers are. And then think of the arithmetic. So the other answer then should be 2 pi minus that inverse cosine of negative 1/4 reading. Because this distance right there is the inverse cosine of negative 1/4. And then what we have to do is take that away from 2 pi to find that other answer. So quickly on the calculator. And I'm back. Now I'm just going to punch this. And see, I'm still in degree mode. So what it's going to do is it's going to come back and give me an answer a little past 90 degrees. So back on the home screen, I go inverse cosine of negative 1/4. And I get an answer a little bit past 90 degrees. And then I'm going to take I'm going to take 360 degrees, and I'm going to subtract from it that inverse cosine of negative 1/4 for my other answer, 255. So the problem was given to us in radian measure, and what I did is I just popped out the answers for you in degree measure, though, because those numbers are a little easier for us to think of. So in degree measure, we picked up analytical answers then, approximations of 104.5 degrees, and the other answer theta 1 and theta 2. The other answer 255.5. Okay, that's the way I'd like you to tackle basic elementary types of trig equation solving. All right, let's go ahead and end this segment, and then we'll move on to the next one here in a minute.